So in this lecture, we are going to discuss all the memory-based questions that I have received from thermodynamics. The thermodynamics as a topic is considered a topic where very good questions, very good numericals can be framed. If you look at the syllabus and the concepts that we have to cover in the syllabus, those are not very difficult or very complex. Yes, there are certain topics, there are certain units in thermodynamics which are, slightly complex for students to understand initially, but if they understand it properly from a good teacher, from a good source, I don't think it becomes a problem. The real issue which students starts facing in thermodynamics is in numericals, because the laws, the principles, the equations are not very difficult or complex, but their application are sometimes tricky, because n number of problems can be framed, very good questions can be framed from thermodynamics. And in fact, I'll tell you an interesting thing here, that since IIT JEE also covers thermodynamics, right? Although there is some difference between the thermodynamics of JEE and GATE, but there are certain questions in GATE which are sometimes taken from JEE as well. So you can understand that the level of questions in thermodynamics GATE can really go up. But this year in GATE 2023, I did not see those questions or very difficult questions as far as I talk about the questions that I have received. At this point of time, we don't know how many exact number of questions were there and how exactly was the wordings of each and every question, but based upon the memory of thousands of students, I assume questions would be more or less the same. From that, I can tell you that the questions of thermodynamics in GATE 2023 were not difficult. Rather, I will put them in the category of easy. They are below average. That definitely I can say. If someone has prepared correctly, has basics clear, these would be very easy to solve. And let me warn students, those students who maybe are attempting GATE 2023 for the first time. GATE 2023 is their first GATE attempt, and they have not prepared much, they have not solved good questions, and they may get a wrong impression that array, thermodynamics is very easy, yaar, it's very doable. मुझे तो आ गई पूरी thermodynamics. I know everything now in thermodynamics because I could solve these 4 or 5 easy questions. So don't make that wrong impression. Okay, next year questions can be drastically difficult or different, which can show you the reality. That is why never ever make the assumption of your level in a subject just by looking at 1 year's GATE paper or your first GATE paper. Okay, now let's start discussing the questions. Now, before I start discussing this question, let me tell you that this is a memory based question, which means actual language wording of the question may differ from this. So if you are looking at this lecture maybe after a week, after a month, after a year, please note language may change, but the concepts that I am going to discuss, they will remain highly relevant. You must go through them even if you are trying to solve any other question from this topic. The question says that in a fully insulated, first keyword, piston cylinder arrangement, piston is massless with a cross section as A. Initially air with a specific heat ratio of gamma is present in the cylinder at a pressure of P1. P1 is more than P0, which is atmospheric pressure, and it is supported by a stopper S1. So far question is pretty much self-explanatory. Piston cylinder arrangement, there's a piston which is massless. Obviously, if the pressure inside the piston is more, if you have a piston cylinder arrangement and the pressure inside is more than the pressure outside, correct? I'm not considering the weight, massless, correct? So it will have a tendency to move up, correct? It will try to expand because on the same area more pressure is acting from the bottom, so net force from the bottom is more than the net force from the top, which will make it move up. Similarly, if this is a horizontal piston, then same thing we can say that if this is P1, this is P0, it will have a tendency to move outwards because P1 is more than P0, correct? To ensure that does not happen, you need to stop it by some stopper. Again, stopper, using stopper in a piston cylinder arrangement is something which has been discussed so many times, theory as well as in numericals across different courses. That's why I told you I consider such problems easy problems, because they are not something which is, we are looking for the first time in GATE, right? I'm sure you have came across such type of problem multiple number of times. So this pressure, this piston needs to be stopped at its place with some stopper, right? So we may use some stopper here to ensure that this piston does not expand. That is the stopper that this question is talking about, and it is calling the stopper as S1. So stopper also has a name, S1, okay? Why it has a name and why we have written it as 1, you will understand once we proceed in the question. So it says that this stopper is removed instantaneously. Very important keyword. This stopper is removed instantaneously, due to which what will happen, you can predict it. If you remove the stopper instantaneously, it will expand suddenly, correct? That won't be a slow gradual expansion, but a sudden expansion, which is not a quasi-static expansion, correct? That expansion we can say is not a quasi-static, but you can say irreversible expansion is going to happen there, because suddenly you have removed the stopper, suddenly it will expand, correct? I am not going into the details of quasi-static versus reversible here, that we already know, right? I am trying to keep the discussion aligned with this question and not going into a direction which is right now not required. So the stopper is removed instantaneously, due to which gas expands, you can say suddenly, and piston is again stopped. Then again it is stopped. How? Another stopper they may have used, right? After S1, when it expands, another stopper S2. Did it mention S2? Okay, it did not. In the diagram you will see, this question also has a diagram. Even if it was not having diagram, you have got the idea what is going on. So it is stopped by another stopper S2. Now, when it expands, pressure is going to decrease, right? Initially pressure was P1. If it expands, if you don't allow complete expansion till the dead state, but you allow it to expand and stop it, its pressure will definitely decrease from P2. So it reaches a pressure of P2, right? Which is more than P0, but is less than P1, correct? Now, it says that determine work done by the piston on the atmosphere. Very important line of the question. We know that whenever question is asking you work done, heat transfer, all these things, it's extremely important to know that who is doing the work, on whom, and what question is asking you. It can absolutely change your answer, right? It can change the magnitude of your answer also, and in many cases it can keep the magnitude same but simply change the sign, right? Which will result in an incorrect answer. If you don't judge this correctly, even if you solve everything correctly, suppose in some of the questions, but still answer will have a negative sign, that's a possibility. That is why this word, this line is extremely important. Question is not over yet. Question also gave you, I think, diagram and options. Again, we are not sure, it's memory based. I have received some question from the student where diagram was not there and these lengths L1 and L2 were mentioned in the question. And I also received some version where diagram was there. Nonetheless, we know that lump sum, this is the question that we have. So as I told you, P1 pressure stopped by S1, allow it to expand, and then S2 stopper is there. P0 is the atmospheric pressure which is working against the piston throughout this motion. Here also, what was the pressure on the outside? Atmospheric pressure. Here also, atmospheric pressure, right? And the option gave you, and the question gave you 4 options, A, B, C and D, right? You can read them. Point here is, so L1 and L2 are lengths. As you can see, this length here is L1, this length here is L2. Now, before I start discussing this question, tell me if in this question massless was not mentioned, and piston was having some mass, will the answer change or not? Think. In this question, I have not even started discussing the question, but let me tell you something, let me rather revise you something, that in horizontal cylinder, piston cylinder arrangement, mass of the piston is not going to affect your pressure calculations because it is not vertical. Pressures are going to act. P1 is going to act in this direction, correct? P0 is going to act in this direction on the piston, But weight is going to act in the downward direction, correct? So when you are writing the equilibrium equations for the pressure, weight will have zero component along that. So even if the piston was having some mass, pressure calculation is not going to get affected by that. So in this question, even if piston is having some mass, your answer is not going to change here. Now, moving ahead with the discussion. Look, this is a question where students need to recall what is the basic concept of thermodynamics and such piston cylinder arrangements, which we have discussed multiple number of times in theory as well as in numericals. Question is asking you work done by the piston on the atmosphere. By the piston, this is the piston moving. And what work this piston is doing on the atmosphere, Now so far, your view is aligned on this gas. You are focusing on this gas. That this gas is expanding, this gas is compressing, maybe. Remove that. Remove this gas out of the scene. Remove it. Don't think about it. Rather, you start thinking about atmosphere. Forget about the gas forget about the air in the piston cylinder arrangement. Rather, you start thinking about this gas. Which gas? Atmospheric gas, which you have. Correct? Question is asking you how much work piston is doing on this gas, on this atmospheric gas. So I am just coloring it and I am showing it. That question is asking you that this little piston here, how much this piston is working, how much work that piston is doing on this atmospheric gas. So on this right side of piston, which is pushing the atmosphere, pressure is P0. Question is asking you, how much is the work done by the piston on the atmosphere? Suppose I am the atmosphere. Suppose I am this atmosphere and piston is doing some work on me. My pressure is not changing. My pressure is P0 only. But the piston has pushed me slightly. Correct? If there is a piston, I am the atmosphere. Suppose I am atmospheric air. I have changed my physical state from solid to consider it to be solid to gas, and I am surrounding this. The piston moves. I am at a pressure of P0. Piston is trying to push against me and it decreases my volume slightly. Correct? If question is asking you how much is the work done by the piston on me, what will I say? What will I say? That my pressure has not changed. My pressure is still P0, but my volume has been slightly reduced. Correct? So if it is about work done on me, I'll say pressure multiplied by change of the volume. I'll say that much is the work done on me because pressure is not changed. My pressure is not changed, but my volume has been slightly reduced. That's how I can calculate it. Correct? So P0, which is the atmospheric pressure, multiplied by change of volume. That's the expression that we know. Correct? That's one way to look at it. That will give you the answer also. Let's have another way to look at it. This was an unconventional way to think of the problem. It's not a conventional way to think of this problem, right? You know that. The conventional way to look at this problem is to revisit the basic expression that we all have covered, the basic expression of work done. And in that work done, remember that this piston and the gas inside this piston is pushing it in this direction, correct? But the question is not asking you the work done by the gas on the piston. It is not asking you. So whatever is going on inside, pressure is changing from P1 to P2. It is adiabatic. It is insulated, correct? So we can write down the expression of adiabatic work done by the gas on the piston. Gas is pushing this piston, correct? So adiabatic work, because this all is insulated, done by the gas on the piston, that you can calculate from the expression of adiabatic work. That one may try to replicate this process. Please note, it is irreversible, but we know that irreversible processes can be replicated by their reversible counterpart and we can get the expression. But is question asking you that? Is question asking you the work done by the gas on the piston? It is not asking you that. Question is asking you work done by the piston on the atmosphere. This piston, how much it did the work pushing the atmosphere. I have already discussed this. Now, keeping all this discussion aside, forget about all this. Just remember what I taught you, what I told you. That whenever you have a system at equilibrium, whenever there is an equilibrium, then you may use the internal pressure also to calculate the work done, whatever such works are asked. But if there is non-equilibrium situation, then resisting pressure or external pressure is used to calculate the net work done. Correct? You remember the free expansion, right? There is no resistance, so work done was 0. Correct? When there is no resistance, work done is 0. Why? Because resisting pressure is absent. So remember those concepts which we have already discussed. Free expansion also is an irreversible process. Correct? This also is an irreversible process. Suddenly, instantaneously it is done. So even if you connect this concept with the concept of free expansion, you can get to the answer. You can understand that we don't have to consider this process, that P1 is expanding and internal pressure has changed. That you don't have to worry about. You have to consider the resisting pressure, the external pressure, right? So I think whatever I taught you, I have repeated here and I have explained that here, because maybe here on YouTube, some of the students might be watching me who have not watched me in the course, right? So that's why this explanation will help both the students, those who have watched me explain all these concepts in the course, as well as those who may not have watched me in the course. But this will give you the idea that in this situation, while calculating the work done, external pressure needs to be taken. And since external pressure is not changing, it is P naught, work done can be calculated by external pressure P naught multiplied by change of volume. How do you calculate change of volume? Cross-sectional area is given as A, correct? So initial volume is how much? Initial volume is how much? Initial volume is A multiplied by L1. Correct? This much cross-sectional area A multiplied by L1. So this is your V1. And final volume or V2 is A multiplied by L2. Correct? Work done is change of volume multiplied by resisting pressure, external pressure, for the situation when there is non-equilibrium situation on the either side of the piston. V2 value AL2 minus AL1. You take out the common, you will get P naught A L2 minus L1. P naught A L2 minus L1. Option B is the correct option for this question. I will again repeat. This is a memory based question, okay? Small changes of the wording here and there, especially here, can totally change the answer. So if maybe in a week, in 10 days maybe, actual question will get via response URL. There we may have a different language, slightly different language. Maybe answer can change if this line is changing. But I'm sure that this discussion told you that what the concept is behind this solution and how this thing works. Moving ahead to the next question. Now this question also is interesting. It is easy, but interesting is the word. Why? If you remember, GATE generally does not ask questions based upon mole calculation, correct? Because calculation of moles and the thermodynamics which deals with moles is microscopic thermodynamics. But the thermodynamics, engineering thermodynamics that we study is macroscopic thermodynamics. But still, this is something which couple of times GATE has asked, and I clearly told and taught this in course, that in video course as well as all the courses where questions are there, question bank, test series and all, that it is very much possible that GATE can ask you questions based upon mole. Don't consider it out of syllabus. There are certain students I found who do not even know the basics of moles, who don't feel comfortable whenever moles come, correct? Because we are happy to deal with mass, right? In engineering thermodynamics, we deal with mass. It is macroscopic, not microscopic thermodynamics. So they are comfortable with mass. That whenever we discuss question on moles, they think, "Arey, it is out of syllabus. GATE is not going to ask. It was asked many years ago. GATE will not ask it now." I clearly told you it can be asked any year. We discussed this, not only the theoretical part but the numerical part as well. So I'm sure this question is going to be very easy. It is based upon the most basic expression of microscopic thermodynamics when you talk about moles. What is that? Number of moles. Number of moles is equal to given mass divided by molar mass. Correct? So this is the expression that we are going to use here. Now the question says that a mixture of two ideal gases, not one but two gases are there. It is kept in a rigid container of 10 meter cube volume. So this is a volume at pressure of 100 kilopascal. This is the pressure. And some of the students of mine have told me that, sir, this is 10 kilopascal also. So we don't know the exact number. Memory based, memory based. So if number changes, answer will change, but concepts that I discuss, they will be relevant and important. So pressure 100 kilopascal and temperature is 300 Kelvin. So P, V, T are known, very rare, right? In a thermodynamics question, I am telling you, it's very rare that you will find all these three things in a single question given, because you know that you can relate all of them using the ideal gas equation. It becomes very easy if three are given, and it actually is an easy question. If molar mass of gas A is 10 kg per kilomole, molar mass of gas B is 20 kg per kilomole, mass of A is 2 kg, how much is the mass of gas B in kg? That's it. Very easy question. Apply the ideal gas equation, find out the number of moles. Number of moles in that system or in the mixture is equal to number of moles of gas A plus number of moles of gas B. Correct? PV is equal to nRT. PV is equal to nRT. R value we know. Universal gas constant. Here you don't have to confuse with characteristic gas constant. If you use PV is equal to mRT, then that will be characteristic gas constant. We have done the derivation of this, right? So I'm sure you know the difference. So R value is constant known to us, T is known, P is known, V is known, N you can calculate. N is number of moles in this mixture. Number of moles in the mixture means total number of moles means number of moles of A plus number of moles of B. Number of moles of A is equal to mass of A divided by molar mass of A. And similarly for B also, just put the value, get the answer. As simple as that. I also will put this question in the category of easy to average, easy to moderate, between that only, because some students may feel uncomfortable when they see mole, especially those who have not paid attention to what I keep telling. Otherwise, it's an easy question. So if I just quickly show you the calculation, PV is equal to nRT, put the values, I'm putting the value with the units so that you don't get the confusion. That's one point where many mistakes are possible if you are not careful with the units. Pressure 100 kilopascal, volume meter cube, number of moles, we'll see the units. This is unit of R, universal gas constant. So if you put joule, then you will remove kilo from here, from both. So joule per mole Kelvin or kilojoule per mole, kilojoule per kilomole Kelvin. Okay, multiplied by the temperature. If you notice here, unit wise this kilo will cancel out. So eventually this kilo will remain. Right? So when you solve it, you will get the value of N, number of moles in kilomole, right? So once you solve it, you will get N is equal to this much. As I told you, N is Na plus Nb. So this is equal to 0.4009 kilomole. Na is equal to given mass by molar mass. Nb is same for B. Here mass of A is known to us, 2 kg, correct? Molar mass is 10 and for B molar mass is 20. Just put it here. 2, 10, 20, MB is unknown. Put the value, get the answer. As simple as that. So be comfortable with these calculations. There are certain more one level or two level up concepts in molar calculations. Make sure you are comfortable with them. Don't ignore them. Don't consider them out of syllabus. I have already taught about these and I already warned you about these, that be comfortable in such questions. Coming to the next question from thermodynamics. A question which I will 100% put in the easy category. It is such a concept which is, I'll say, ABCD of engineering thermodynamics, right? Directly based on most basic expressions of first law and second law. I am sure if you are someone who even just covered ABCD, you should be able to solve it easily. It has been discussed across different courses, right? I am sure. Question says that there is a heat engine which receives heat from a thermal reservoir at a temperature of 1000 Kelvin. So the source temperature is 1000 and it rejects heat to a thermal reservoir at a temperature of 100 Kelvin. So the sink temperature is 100. Taking heat from 1000, rejecting to 100. Obviously, it's a heat engine, will be doing some work also. Which values of QH, QL and W are correct? Four different values are given, 4 different set of values are given. You have to tell which one of them are correct, or in other words, which of them are valid or are possible, right? Different terms can be used in the question. Maybe question also gave you a diagram. If the diagram was given, it will look like this. If diagram was not given, then QH, W and QL will be defined in the question. You see in the question, as such, what is QH, what is QL, what is W? It is not written, right? Because the question, the version that I got, in that version, many students showed me like this with a diagram. If diagram was not there, then QH, W and QL would be defined, because whenever there is a diagram in the question, it is possible that some terms may not be explained or defined in a question, right? Every variable which is used in the question, in the option, should be defined by the question, ideally. So if that is not done, maybe that is done in the diagram, okay? If not in the diagram, it should be in the question. So you got the point. So this QH is the heat which it is receiving from source. QL is the heat which it is rejecting to the sink. W is the work output which this heat engine is doing. Now we know that to relate these three values, we can use definitely first law, because whatever heat it receives should be, or whatever energy it receives should be rejected or should be given out as work, right? The first law of conservation of energy, correct? So QH is equal to QL plus W. Coming to the second law, because only using first law, you may not be eliminate everything. Let's rather try first before moving to second law. Maybe by just using first law we can eliminate and get the answer, right? Because there are certain such questions in GATE 2023. When I was discussing questions live, I told one question of fluid mechanics which you can solve without lifting the pen and save 2-3 minutes of your time, right? 3 options can be eliminated just by using your concepts, which happens but not happens very frequently in GATE. But students whose basics are clear, who have covered all the concepts from me, like from zero, I am sure for those students such questions, the question of fluid mechanics I am talking about, would be very easy. Similarly, in such questions of thermodynamics, if you have 4 options, generally what happens? In any question, you get the data from the question, you solve it, and then you tick the correct option or correct options, right? But here, in such questions, you eliminate it. You cannot answer just by the data of the question. It's not possible that if I just gave you the data of the question and tell me whether A will be, which option should be correct, right? The data itself lies in the option. You have to move ahead by elimination process. You have to judge each and every option and eliminate it or select it. So let's see how many options we can eliminate just by using the concept of first law. Then we'll come to the second law part. So here, checking for first law, which is this. So the value of QH in the first option I have written directly here, correct? So basically this value QH, as we know, should be equal to QL plus W. That's the thing that you'll have to do. As simple as that. If you add QL and W, you will see option A is not going to be true because it's not same. Option B will be true because QL plus W, 500 plus 5500 is 6000. Similarly, doing this for C and D, I am not saying it, it's just basic maths addition and just checking if it is same or not. So for option B and for option D, you can see that QH is equal to QL plus W. Now, I'm not sure whether this question was asked as MSQ or not. But let me tell you, if this question was asked as MSQ, at least 20% students, I can say 1/5 or 1/4 students who have not paid attention, who have not even covered ABCD, they will tick B and D. They will say, "Arey B and D match ho gaya." For B and D, first law is working for B and D. It is true. They will not even apply second law. They will think, "Arey, MSQ hai, it should be more than one," which is wrong. MSQ can also have one correct option. So don't have this misconception that MSQ should have more than one options correct. I know some students still in this confusion, even though MSQs have been introduced now for years, 2-3 years. So please note that you have to move ahead and complete the calculation by considering the second law as well. So as per the Clausius inequality statement of the second law, we know this expression, correct? For this case, where we are going to apply it for heat engine, because it is going the cyclic process, right? So this closed loop integration for heat exchanger del Q by T is less than equal to 0. If it is more than 0, it is impossible, right? It should be less than 0. Again, if it is only less than 0, then it is irreversible. If it is equal to 0, then it is reversible. Question is not asking you reversible or irreversible, right? If question has mentioned a reversible heat engine here, then you will have to directly check equal to sign, not less than equal to, directly equal to sign. It's not mentioning whether it is reversible or irreversible. It's simply saying by heat engine, whether heat engine is possible or not, right? So only this condition you will check. If it is verifying, means it is possible that those set of values would be correct. So here, for this heat engine, this expression would become QH divided by higher temperature, and it is receiving that, so with a plus sign, minus QL divided by 100. And this should be less than equal to 0. So this is the statement that we need to check. For whose options? Not for option A, not for option C, but for option B and D, for which first law is getting valid, right? If we do that for option B and D, let's start with B. This is QH value, this is QL value, this is W value. Putting the value of QH and QL here, 6000 by 1000 minus 500 by 100 is less than equal to 0. Means this is 6 minus 5, which is 1, which is less than equal to 0. No, 1 is more than 0. So this is eliminated. Option B also is not correct, which obviously means option D is correct, right? So even if you have eliminated 3, yes, you can check, cross verify your answer by doing the calculation for D. But if rest 3 calculations are right, means this obviously would be correct. It's a matter of, you can say it's a matter of luck, right? For some of the students, maybe the first option itself, suppose this was an MCQ, and it is an MCQ, I think. So if it is an MCQ, you started testing from the first option, and first option itself, you know, checked for first law as well as second law. Good luck. For some of the students, even the last calculation you have to do till you can get the answer. So it's a matter of luck here, but the question itself is very easy. Hardly it will take, what, 1 minute, 1.5 minutes, max 2 minutes to get the answer. So I'm sure almost all of you have done this correctly. Now, another question from thermodynamics, a theoretical question. Please note that time and again GATE asks theoretical questions from certain topics of thermodynamics. Rather certain very specific topics of thermodynamics. They are real gas, ideal gas, reversible process, irreversible process. It is certain thermodynamic relations between pressure, volume and temperature. These are 2-3 topics from which you can expect theoretical questions a lot more as compared to theoretical questions from other topics. Same is true for this question also. Here 4 statements are written, and you have to tell which of the following statements is false, right? I think 10, 20, 50 times I have told you, whenever you see a statement asking you false, be extra alert. In your scribble pad, write in caps in your scribble pad, F-A-L-S-E, so that you don't forget you have to tick the false ones. Because since when you are solving MCQ question, 99% question you have to tick the true ones, right? The answer that you got, something which is true, which is correct. So out of habit, even though you read false, you forget. You end up ticking the correct ones and you move to next, and then obviously it's a negative mark. So what we'll do is we'll go one by one with the options, okay? Option A says ideal gas enthalpy is independent of pressure. Quick, very easy. Enthalpy, H is equal to U plus PV. For an ideal gas, we know that internal energy is a function of temperature. For an ideal gas, PV, again you can write as mRT, where it is constant, this is constant, and this is temperature. So both of these terms are function of temperature, which means enthalpy is a function of temperature. Again, it is not something that I should be explaining here. I consider this like ABCD of enthalpy only, but still, it is independent of pressure. It does not depend upon pressure, it is independent of pressure. It depends upon temperature, correct? So this statement, ideal gas enthalpy does not depend upon pressure, is true. So will you tick it? No, you won't tick it. You have to tick false, tick if false. So you won't tick it. Moving ahead to the next one. For an ideal gas undergoing a reversible polytropic process, PV to the power 1.5 is equal to constant, right? This is the standard notation, standard process equation, governing equation for polytropic process, reversible polytropic process, where n value is 1.5 here. It is saying that for this process, equation P by R is equal to mt by V is valid. What is this equation? P by R is equal to mt by V. Looks like very familiar equation, slightly arranged in a different way. If I write PV is equal to mRT, it is the same old ideal gas equation. Obviously, if the gas is ideal gas equation you can apply, right? It won't matter whether this process is having PV to the power 1.5 or 1.4. So definitely this option is correct. So I won't tick it. This is tick if false. So this is also incorrect. So option A gone, option B gone. Coming to option C and D. This option was also an ideal gas. This option was also an ideal gas. You may get an idea that array, it's an ideal gas only. Don't do that, because next two options are not on ideal gas, they are on real gas. So be very alert. At sufficiently low pressure and high temperature, real gases behave as an ideal gas. Extremely true. We have discussed this. C is correct, which means I will not tick it. Tick if false, right? When the pressure is low and the temperature is high, the real gases tend to behave like ideal gas, right? Even in the property diagram also, in the graph also, there's a region that we call as, this is the region where the ideal gas behavior will be shown by the real gases. Moving ahead to the final option D. For a real gas, again real gas, going through an adiabatic reversible process, PV to the power gamma constant is applicable. We know that for reversible adiabatic process, PV to the power gamma is equal to constant. Definitely we write in gamma is your specific heat ratio, but this expression, this derivation is done for ideal gas, not for real gas. For real gas you cannot say this expression to be true. Simply you can recall the derivation of this process, which will tell you that. Hence option D also is incorrect, which means here you will tick it. You have to tick it if it is false. So D correct, C incorrect, B incorrect, A incorrect. So here this is the correct option for this question. I think this is a question where small silly mistakes may happen in reading incomplete statement, or this one, the biggest one. Otherwise this question also I will rate it as easy question, but since some silly mistakes are possible, it can be between medium, between easy and moderate level. So I'm sure this gave you an idea of the types of questions which were asked in thermodynamics. These are the questions so far that I have received. Please note, as I told in the beginning, questions, none of them I will say above average. Don't get the wrong idea. Don't think कि अरे thermodynamics आ गया मुझे. If you solved, if you attempted 2023 for the first time, I'm sure you will feel कि you are an expert in thermodynamics. Please don't get overconfident. Whenever get asked easy question, students become overconfident. Whenever get asked difficult question, they become underconfident. Be realistic. Live in reality. Understand that thermodynamics can have superb questions for which you need to have basics as well as advanced concepts, mastery in those concepts and mastery in solving the questions. I wish you all the best.